Lesson 12, Neutron Radiography. Introduction to Neutron Radiographic Testing. In the radiographic testing lesson, we discussed the use of X-rays and gamma rays to see and evaluate a test specimen's volumetric subsurface as a film or digital image. However, there are additional means to capture a radiograph using low-energy thermal neutron particles. Although similar to X-ray and gamma ray radiography, neutron radiography testing, abbreviated NR, is a separate NDT method that evaluates structures somewhat differently and displays unique internal characteristics that would otherwise be difficult to interpret using other NDT methods. Solid metals appear nearly transparent with neutron radiography, as when analyzing hydrogenous materials as part of a composite-type structure or assembly. Although neutron radiography got its start in the mid-1900s, the technology took many decades to mature and migrate out of academic research and government experimentation and into the profession of non-destructive testing. Even today, neutron radiography has limited applications, but is slowly finding its way into more applications, especially where imaging using conventional X-ray and gamma ray is not possible. As we discussed in our lesson for radiographic testing, the way in which X-ray and gamma radiation photons interact with the atom's electrons and attenuate in a test object determines the contrast of a radiograph. The greater the contrast, the more readily observable the discontinuity. Neutron radiography attenuates much differently in a material to provide a different visual display on film or digital media. The discriminator in neutron radiography is the neutron attenuation by the test object's nucleus. The larger the neutrons in the nucleus, the greater the attenuation. It is this attenuation difference that makes neutron radiography advantageous to conventional radiography for not only imaging hydrogenous materials such as water and hydrogen, but also for penetrating heavier elements such as lead. In determining whether neutron radiography will complement existing RT requirements and variables, such as cost, quality, mobility, neutron yield, and time must be taken into consideration. Advantages of neutron radiographic testing. Penetration depth is not impacted with heavier materials like lead, iron, and titanium. Neutron radiography can observe hydrogenous materials such as water, plastics, and rubber. Limitations of neutron radiographic testing. There are limited applications. Sources of neutrons from bombardment are limited and can be expensive. It can make test objects radioactive. Neutron sources. As might be expected, a source of neutrons is required to conduct neutron radiography. Neutrons are produced from the following three sources: radioisotopes, neutron accelerators, and nuclear reactors. Radioisotopes. As we mentioned in radiographic testing, the number of protons in the nucleus defines the element. An atom with 1 proton is a hydrogen atom, whereas an atom with 6 protons is a carbon atom. Since atoms prefer their nucleus to be balanced, the number of neutrons is typically the same as the number of protons. The number of neutrons is important to balance the stability of the nuclei. As the ratio and balance of neutrons to protons increases, the nucleus becomes unstable and emits radiation in an attempt to become stable. This atom stability process is known as radioactive decay, and the element is called a radioisotope. There are two types of radioisotope sources that require fission, meaning the splitting of atoms, and those that produce neutrons due to alpha particle or gamma ray bombardment upon the nucleus of certain elements, like beryllium. One of the major radioisotope neutron sources used in NDT is a manufactured element called californium-252. Californium spontaneously undergoes a fission reaction that releases neutrons at a fairly moderate energy level of 2.3 MeV. Although fairly expensive, californium is the preferred radioisotope source for neutron radiography due to its high-volume neutron output, low emitted neutron energy, half-life of 2.6 years, and small physical size. Americium-241, combined with beryllium, is another neutron-emitting radioisotope. However, instead of fissure, beryllium is combined with americium-241, which is the isotope, in order to subject the beryllium nucleus to alpha particles to produce neutrons. Americium-241 combined with beryllium has a half-life of 432 years in the 2 to 10 mega-electron-volt range. Neutron accelerators. Neutrons can also be generated using neutron accelerators. Hydrogen has 3 isotopes: protium, deuterium, and tritium. If either deuterium or tritium isotopes are accelerated towards a deuterium-enriched target, the resulting collision of either deuterium and tritium or deuterium and deuterium fuses the two isotope nuclei together. This is known as a nuclear reaction. A nuclear reaction generates byproducts of radiation energy, helium or helium isotope, and a neutron. It is this free and accelerated neutron that is used for neutron radiography. Of course, more than one neutron is required for neutron radiography. A single nuclear reaction must be multiplied by billions to generate enough neutrons for industrial radiography applications. The deuterium plus tritium neutron generation produces an output of approximately 14 megaelectron volts, and the deuterium plus deuterium neutron generation produces approximately 2.5 megaelectron volts. The advantage of neutron accelerators is the fact that they can be turned off and on, but generally require substantial startup costs on equipment and infrastructure. Nuclear reactors. Nuclear reactors also produce neutrons due to a chain of fission reaction of uranium-235. When a new neutron is introduced to uranium, it makes the nucleus of the uranium unstable and spontaneously splits to form two new lighter elements such as krypton and barium, as well as discharges 3 neutrons. These 3 neutrons then impact more uranium-235 nuclei to create a chain reaction of ever-decreasing lighter elements and incrementally increase the quantity of discharged neutrons. As one can imagine, on a grand scale of billions of fission reactions happening near simultaneously, the quantity of neutrons can increase very rapidly. Neutrons obtained from any of the aforementioned sources are emitted extremely fast and orientated in a scattered haphazard array. To make the neutrons useful for neutron radiography, they must be slowed down and channeled into a stream towards a test object. Step 1. Slow the neutrons by a moderator. Neutron radiography requires slow, low-energy neutrons for optimal image contrast. A moderator, such as a pool of heavy water, is used to slow or lower the neutron energy. Once slowed, the neutrons are deemed as thermal or cold, depending on the level of energy drop. Step 2. Extract and funnel neutrons with a collimator. The moderated and slowed neutrons are scattered in all directions. To make the neutrons usable, they must be extracted and funneled towards a test specimen. To do so, a collimator is used to produce a parallel beam of radiation. There are generally 2 types of collimators used in neutron radiography, a multi-tube and divergent. Multi-tube collimators can be visualized as a tube inserted in the moderator with one end near the neutron emission source, while the other end is outside the moderator wall directionally facing the test object. As the steady stream of neutrons channel through a tube, any neutrons not parallel in the tube's neutron stream will eventually hit the tube wall and be absorbed by boron, cadmium, and gadolinium coatings. Divergent collimators can be visualized as a cone-type funnel. The small hole end is near the neutron emission source in the moderator and then gradually diverges to a peak circumference directionally facing the test object. As with multi-tube collimators, the cone is lined with boron, cadmium, and gadolinium to absorb scattered neutrons and keep the neutron beam steady and parallel. Interaction between neutrons and matter. After acquiring the neutrons needed, the test object is placed between the neutron beam and the imaging media. As free neutrons penetrate a test object, they encounter and impact the nuclei of the elements within the test object. Some of the elements in the test object will be heavy and dense, such as iron with a high atomic number, while other elements will be lighter, smaller atomic numbers such as hydrogen. Neutrons are more likely to impact and attenuate with the larger nucleus of lighter elements. When they impact the nuclei of an element, neutrons can be absorbed, scattered, or both. Absorption. Slower-moving neutrons can be absorbed by the nucleus they impact. This absorbed neutron in the receiving element nucleus creates a new isotope and increases the mass by 1. As an example, if a cobalt-59 nucleus absorbs a neutron, it becomes cobalt-60. By adding the neutron to the nucleus, it becomes radioactive and releases a beta particle and gamma ray as it decays. Neutron absorption reaction is very useful in neutron radiography techniques for many applications. Scattering. Faster-moving neutrons exhibit scatter and may be either elastic or inelastic. Elastic scattering occurs when a neutron collides with a nucleus and then loses its kinetic energy. Similar to how in a game of pool, a struck pool ball loses its kinetic energy. The lighter the nucleus of an element, such as hydrogen, the greater the loss of kinetic energy. Inelastic scattering. Inelastic scattering is similar to elastic scattering, except the remaining kinetic energy of the neutron excites the nucleus to a higher state and gives off gamma radiation as it returns to its ground state. Inelastic scattering is not desirable in neutron radiography due to the gamma ray interference of image acquisition. Energy conversion techniques. After passing through the test object, the neutrons must be converted into another form of radiation that can be detected and measured for imaging. As with gamma and X-ray radiography, image acquisition with neutron radiography can be made by film or digital media. After neutrons penetrate and pass through the test object, they impact and interact with a converter screen to produce a radioisotope, alpha particles, or light, which converts the energy to an image on radiographic film, an imaging plate, or optical camera, or a video camera. However, the image medium selected is dependent on the energy conversion technique. Two common neutron radiography converter screens are metallic foil screens and light-emitting screens. Metallic foil screens convert neutrons to beta particles, gamma rays, and conversion electrons. Gadolinium is considered to be the best metallic foil screen for high contrast and resolution. Light-emitting screens, in which neutrons interact with a scintillator or phosphor-lithium or phosphor-boron screen to image light received from expelled alpha particles. Neutron radiography testing image analysis. Neutron radiography complements gamma ray and X-ray radiography to provide an image that is somewhat layered. Neutron radiography allows technicians to see clearly lighter elements, such as liquids, rubbers, and plastics, against and in contrast to denser materials, such as steel, aluminum, and titanium, which appear nearly transparent. Neutron radiography is particularly sensitive to the detection of hydrocarbons inside metal containers. The left image shows an example of detecting gunpowder in rifle rounds using neutron radiography. The right image shows an X-ray of rifle rounds where the level of powder is undetectable. This is due to the high X-ray energy needed to penetrate the dense casing, which is too high to clearly identify the soft propellant inside. The left image shows the detection of the gunpowder where the neutron beam easily penetrates the metal casing, but is highly sensitive to the hydrocarbon material inside. The level of fill is readily detected in the neutron radiograph. This capability is routinely employed in critical aerospace and military hardware, such as satellite development systems, explosive bolts, ejection seats, and multiple styles of military projectiles. And that concludes this lesson.